Okay. I would like to thank the organizers, especially the Dr. Professor Ali Ganjar and his team who made this conference possible in very hard times. So I will just talk about the ferrites. These are the economic synthesis and the multi-domain applications. I am from Pakistan. So at the moment, some views of the university in which I am teaching. Mostly our group is working on the materials. We characterize, synthesize and characterize using the simple methods, rare earth materials, ferrites, thermoelectric materials and fibers. So just going through a brief introduction, then I will go to the structural classification of the ferrites, since how these were synthesized, and then we come to the results and the discussion. Ferrites are basically ceramic materials that contain iron as a major. The reason to select ferrite material is we can optimize, tune them according to our need. These are non-toxic and low cost and dopant, and we can vary the properties by varying the concentration of the dopants. Ferrites would be classified in two categories. Either we can classify them according to their crystal structure or according to their magnetic response. According to the crystal structure, we can categorize them as spinel ferrites, hexagonal ferrites, garnet ferrites, orthoferrites, and when we talk about the magnetic property, then these could be classified into soft ferrite and the hard ferrites. Mostly the soft ferrites are spinel and garnet in structure. They have low coercivity, low magnetization, small hysteresis loop, and hard ferrites are usually hexaferrites and orthoferrites in structures. They with the high coercivity, large magnetization, and large hysteresis loop. Applications of ferrites. There are a number wide variety of the ferrites applications. These could be used in electronic devices, as memory devices, as AC and DC power devices, in the medical equipment, in microwave absorbers, in cores, in lithium-ion batteries, and also in data storage devices. Another class of materials are the rare earths. The rare earths have various applications varying from the catalysis to glass dyes in automobile catalysis and different pigments that could be used as phosphors and in other applications. So we are going to talk about the combination of the ferrites and the rare earths for the useful applications. Synthesis techniques, bottom up and top down. Bottom up usually are economic and these could be easily handled. The materials we have prepared are prepared by two wet chemical methods. First one is the co-precipitation method. The nitrates of the respective elements were dissolved in the deionized water with the molarity of 0.4, and then these were heated at 75 degree, and then after getting the precipitates, these are calcined and pellets are made for the further characterization. The beauty of co-precipitation is that we can get the purity, homogeneity, and this is a low temperature method. The other method we have utilized is the Bow sol gel. It is a simplified form of the sol gel method in which we can, in single step and in less time duration as compared to other methods, we can get the pure materials and a very small particle size. Characterizations we have done for the study are the XR, DFT, DSC, TGA, SCM. For the structural analysis, for the thermal conductivity was measured, and for the electrical analysis, AC and DC properties were measured. I will talk two different domains of the application. One is the use of ferrites in the electronic devices, another one is in the energy applications. The first one is their use in the electronics, that is as a memory device. Usually memory devices are classified according to their mortality, access mode, according to the media or information variability. Conventional memory devices are mostly volatile. They are slow speed, expensive, with the poor right endurance, and are power hungry. So emerging non-volatile memory devices are based on four different categories: on the magnetic MRAMs, phase change PRAMs, resistive RERAMs, and ferroelectric FRAMs. So we have studied our ferrites as an possible application in the ferrites. The resistive RAM basically is a resistive switching random access memory kind of memory that is utilizing electric field induced resistance change in the certain kinds of the materials. So the switching is based on the resistance of the material which is varied with the applied voltage. Now coming to the results and the discussion. Structure analysis, we synthesized the first set of material that was cobalt ferrite, and iron was replaced by the lanthanum, gadolinium, and cerium in the uniform proportion. In all the cases, we get the cubic structure with the almost similar lattice constants. The slight increase in the lattice constant is due to the higher radii of the rare earth ions. Now coming to the electric analysis, we have done the dielectric spectroscopy. Dielectric spectroscopy mainly helps to know about the interaction of external field with the electric dipole moment of the sample. Usually there are four polarizations which are being uh, utilized: when the orientation polarization, atomic polarization, electronic polarization, and with the frequency these are dying out as we are increasing the frequency to the higher region. One by one these polarizations could not follow the applied field, and as a result the overall dielectric constant of the material that dies out. Similar trend as we have seen in the principle in the last slide, that as we are increasing the frequency, the dielectric constant of the material is decreasing. We are getting good dielectric constant in case of the gadolinium doped ferrite, and in case of the lanthanum doped ferrites, the dielectric constant was not that good. The dielectric loss was also less in the lanthanum doped samples, and in case of the 10 delta, that is the energy losses, which are basically we are having two humps here that indicate that there are two polarization mechanisms which are dying out in this frequency range. Moving on to conductivity, the rights usually follow the Johnson's power law. Johnson's power law tells us that we have three regions. One is the region 1 is the high frequency region, the other one is the region 2, that is the frequency dependent region, that is in the middle, and region 3, which is a frequency independent in the region. So that as it depends upon the temperature as well as the frequency as we are moving. What actually is happening is that when an ion gets a vacant site, it jumps to the next site, and if that site holds that ion, so that will be there is a change in the potential as is shown in the lower figure, the change in the potential, and this as a result the ion moves on and on, and if that comes back, it means the jump was unsuccessful. So as we are increasing the frequency, more successful jumps are available as compared to at the lower frequency mode. This is known as the jump relaxation model. You see in this diagram that as we are increasing the frequency, the conductivity initially in the frequency dependent region, then it is increasing as we are increasing the frequency, just the similar way as you see in the last previous slide, that as we are increasing the frequency, more successful hoppings are done as compared to the lower frequencies. Impedance is inverse of the conductivity, and it is decreasing as we are increasing the frequency. In the core plots, we can see that the conduction mechanism or behavior in these material is of two type: Maxwell-Wagner type. Double layer model can be applied, that the grains and the grain boundaries are contributing in the conduction of the materials. Applying the current voltage curves, we can see that there is a good hysteresis when we are moving from 0 to positive voltage, and from then higher to lower voltage, and then again from the uh, 0 to the negative voltages. So these hysteresis loops are very much uh, required for the resistive switching and use of the ferrites in the resistive ramps. So concluding the first section, nanoparticles were successfully synthesized. X-ray diffraction analysis confirmed the formation of the spinal cubic structure. Dielectric constant, dielectric loss and impedance decreased with increasing frequency. Cerium and lanthanum results in decrease in the dielectric constant, while the gadolinium there was enhance in the dielectric constant. So core plots indicate the dominant role of the grain boundaries in conduction mechanism, and current voltage curves exhibit non-linear hysteresis loop type, and which confirm the existence of resistive switching effect in the investigated compositions. In the second section, we varied the ratio of the neodymium in the at the iron side to see how that is affecting the properties of the cobalt ferrite. FDA are also confirmed the single phase spinal structure in the cobalt ferrites. Particle type morphology could be seen in the SEM, and in the DSA and TGA analysis, almost in all the cases, the transition was in the region 450 to 500 degrees centigrade. So these SEM materials were sintered at 550 degrees centigrade for further characterization. By increasing the temperature, DC conductivity, DC resistivity was decreasing in all the cases, with the maximum dopant concentration shows the highest resistance as the iron content is lowered, so the resistance increased by the dopant concentration. Similar, this is verified by the activation energy. As the dopant concentration is increased, the activation energy is also increasing. Mobility of the material also plays important role when we are discussing the properties, particularly when using them as a resistive RAM. We see that the concentration with 0.10 shows the maximum mobility, and the maximum dopant concentration shows the least mobility. In this case, as we are increasing the concentration, we can see that there is a hysteresis loop existing in these materials as well. So these could also be used in the resistive switching mechanism. So their thermal properties were lastly investigated by the advantageous transient range source method. That was a system in which a sensor is sandwiched between two identical sample pieces, and then the data is obtained, or as a result we have calibrated the system and compared the data of the quartz, and we see that the obtained data by our system was very much in line with the reported value. So thermal conductivity of all these materials are in the low conducting region or in the insulating region, and accordingly the thermal diffusivity and volumetric heat capacity are also in the lower regions. The thermal conductivity could be directly related to the porosity in this case, that as the porosity increases, the conductivity also increases, and when the porosity decreases, then the conductivity also decreases. Now coming to the summary of the second part, soul gel method was used for the preparation of the material. Cubic spinal structure was obtained, and in SEM we see the particle-like structures. The maximum resistivity was shown by the maximum doping concentration, and thermal conductivity was in the range of 0.215 to 0.325. So these materials could be used as thermal barrier coating at higher temperatures also. In the second section, the application of these materials in the energy sector. Renewable energy sources are demanded very much nowadays, as non-renewable energy resources are depleting day by day, and thermoelectricity is one of the important renewable energy source. So it is based on the Seebeck effect. Our colleagues earlier have told in detail how the Seebeck coefficient and the Peltier effect or the Thomson effect are working. I will not go to in details on these. So usually the half oscillars, fluorides or tellurides are investigated for, or cobaltides are studied for their thermoelectric properties. For the ferrites, we can find very rare literature. We have investigated ferrites to be a potential candidate for the thermoelectric materials. For this purpose, we have selected cobalt ferrite, and on iron side we have used the chromium. We got the single phase cubic structure in all the cases, and as we are increasing the concentration, the lattice constant decreasing due to the reason that chromium has the smaller ionic radii as compared to the iron, so the lattice is contracting. These XRD patterns are indicating the same thing. The other material that was investigated for this was the nickel zinc ferrite. In nickel zinc ferrite, we have varied the concentration of zinc in place of nickel, so to see how that could be that could affect the properties, and in this case the ionic radii is increasing as the zinc ionic radii is higher as compared to the ionic radii of the nickel. Particle-like morphology is observed in the SEM micrograph. Resistivity increases by the decreases by the increase of the temperature, and mobility is higher in the undoped sample, and by the doping the resistivity is decreasing and mobility is also decreasing. Same trend could be seen in the conductivity and the activation energy, that as we are increasing the concentration of the zinc, the activation energy is increasing. To study the thermoelectric property, the Seebeck coefficient of these materials, a simple method, a simple sample holder was designed, and then it was calibrated by using the aluminum and the copper, and we got almost within 5 to 10% difference to the reported values. So for in the case of the cobalt ferrites, we got Seebeck coefficient in the range -250 to 50649, and in case of the cobalt ferrite, we see that this is the plot, as initially it is decreasing and then increasing. In the case of the nickel zinc ferrites, we see that interesting thing, that in this material, as increasing the zinc concentration, we got both p-type and n-type material within the same family of the ferrites. So nanoparticles of cobalt ferrites and were successfully synthesized, all were with the spinel structure, lattice constant increases with the zinc concentration. Some micrograph shows the agglomerated particles. These resistivity composite were done by the 2-pro method. Thermoelectric properties are done as a function of composition. The Sinus-Sieve coefficient shows that all the samples were n-type in case of the cobalt ferrite and of both types in nickel zinc ferrite. At then, I'd like to acknowledge the Higher Education Commission Pakistan, our University ComStats, IRCBM, and particularly to the organizers of the 7th International Conference of the Superconductivity and Mechanism. It has been honored to attend and present in Indian conference, and also I was co-organizing the ferrite session. This year, due to the COVID restrictions, it was not possible to attend the conference physically. Let's hope next time the situation will be better and we will see each other again. Thank you for your attention.
Could you open the graph? I think could you go back? This one. This one. What is the physics this minimum and a maximum on this graph? I mean, this fluctuation. Could you explain the physics on this graph?
Actually, up to the concentration of 0.2, the drift mobility is decreasing and then it is increasing. Basically, it is the drift mobility that is causing this difference to the movement of the carriers.
Okay, there are no more questions. I guess that is related to your doping level that you change. Yes.
Yes.
It may change the. You think it might change the oxygen stoichiometry in the system?
Yes.
And also the defect content, I guess, right, and distribution.
That is the main reason. Actually, the variation in the crystallite size is not uniform, as they are increasing the dopant concentration. It depends upon many factors. Due to the strains and other issues, there is a non-uniform trend in the crystallite size of the material. So that is why that is reflected in the CPEC coefficient as well.
Because as this is a polycrystalline material, you may have an effect on the intrinsic part in the intergranular part, but also in the intergranular junctions, right, between grains, I guess. You could have some concentration of impurities in the impurity phases in there, right?
Yes.
But you have not been able to characterize it, I guess. Whether you have a concentration, an excess concentration between grains, for example.
If the conduction in these materials are quite problematic and difficult to explain. So we are trying to find out what the mechanism actually is going in. So we have submitted a project at the exhaust beamline. Maybe if we get the time, then we can define how the conductivity is controlled by the local structure of the ions within the material. So maybe then we can clearly define what was the reasons for this specific trend.
Okay, thank you very much again.